learned so far, the molecules in the gas are moving at random in all possible directions with equal probability. While the molecules are moving at random, they are colliding with the wall of the container and also with themselves. And the former is called wall collision and later is called the intermolecular collision. And wall collisions I have discussed in my last class and also explained what is meant by the frequency of wall collisions by the molecules. And in that case also one application and one application I have also shown very rare application how the vapor pressure of a metal or saturated vapor pressure of a metal could be determined by Knudsen diffusion method using the formula of frequency of wall collisions. Today I like to explain the intermolecular collisions, and in this case the first I shall explain the collision diameter, means distance between the two centers or distance between the centers of two molecules while they are colliding, and the collision number, means how the number of collisions made by a single molecule with other molecules in the gaseous state in unit time. And next I shall come to the mean free path, means minimum the average distance a molecule can move without suffering any collisions, or in short you can say it is the distance between the mean distance between the two successive collisions. So let us first explain the collision diameter. The collision, suppose this is one molecule and it is its center. We have taken some assumptions. As we have seen in kinetic theory of gas, molecules are a rigid, non-interacting and sphere with the diameter sigma. And also we have assumed the molecules are moving, all the molecules are moving with this average speed c bar. So here it is one molecule and here it is another molecule, and it is its center. The molecules is coming in this direction and this molecule is coming in these directions, and they are touching each other and making a collision. So this is center. This is the distance of centers of two molecules, so while they are colliding. And this distance we call the sigma, and sigma is the collision diameter. So collision diameter, you can say the distance between the centers of two molecules, so when they are colliding. But we can also give some alternative explanations or definitions of this collision diameter. Say here is one molecule Here it is another molecule. As we now all know, the molecules are neither rigid and they are interacting, and the molecules are not in spherical shape. So, if we can modify the definition of the collision diameter, then suppose this is the center and center is the positive charge, and it is the center of this molecule. This is also positive charge. Here it is electron, outer shell electrons. So in this case, whenever these molecules are coming here and this molecule is coming in this direction in order to approach each other, when they are at large distance, relatively large distance, there will be attractions between the nucleus and this electron, and this nucleus with this electron. But when they are approaching close together, then the attraction becomes or the repulsion starts between the molecules, nucleus, positive charge, it will be repelling, and the outer shell electrons, they are also repelling when they are getting enclosed. So, since these repulsive forces, according to the van der Waals assumption, repulsive forces are short range force. It dominate when they are coming very close together, while the attractive force is a long range force, and whenever they are operative when the distance is large. So when the distance is very close, the repulsive force overcomes this attractive force, and this molecule will not come. This molecule will not come beyond this distance. They will not approach beyond a certain minimum distance. And say this distance also we can call this sigma. So it is not necessary that the two molecules will touch while they are colliding. Instead, they may go far apart, fine apart, whenever they are approaching this distance sigma. They cannot come. The centers of these two molecules cannot come beyond a distance sigma. Means that this R will be always less than or equal to sigma. And in physics, you know, the collision is such type of event in which the momentum and kinetic energy are being changed. So this sigma also we can call the distance of closest approach. Distance of closest approach or minimum distance of approach. So this is all about the explanation of the collision diameter. Now I like to explain what is meant by the collision number? Means the number of collisions that one single molecule collide with other molecules in unit time in a gas vessel. So let us explain. And you know the collision diameter for this molecule is very small, in the range of angstrom unit. Means 10 to the power minus 8 centimeter or 10 to the power minus 10 meters. Very small. So let us say collision. Let us explain the collision number. And suppose this is one molecule. Molecule have been taken as spherical in shape for the sake of simplicity, for formulations of our expressions of collision number. And suppose there is another molecule, and when they are colliding, say this is this center. This is the centers of these two molecules when they are colliding. And this distance you can call sigma, collision diameter. And there is another molecule, say another molecule whose center is here. So this molecule is taken our reference molecule, and it is designated by A. And whenever this molecule will move, it will sweep a cylindrical tube with this moving of this molecule, with this movement of this molecule. So to explain the collision tube, which is also called the heat cylinder, let us draw one bigger sphere of radius sigma around this area. This is the area of cross section. And this is equal to pi sigma square. Sigma here is the radius of this outer sphere or bigger sphere. So whenever the center of any molecule will enclose this area of cross section, that molecule will suffer a collision with this A. Say in any directions that molecule may come. Whenever this molecule or center of this molecule will enter into this cross-sectional area pi sigma square, this molecule will collide with A. So let us, whenever this A is moving, it will sweep a cylindrical space, and this one is the collision diameter. This one is also the area of cross section of this molecule A. Any center of this molecule, any center or center of any molecule when enters into this tube, into this cylindrical tube, this molecule will suffer collision with A. And this is why this is called heat cylinder. Heat cylinder. And for making this formula in a simpler way, let us first take a supposition that this molecule is moving, A molecule is moving with this average speed c bar, and all other molecules are assumed to freeze at its own position in space. They are not moving, they are at rest. Only one molecule is moving. This is a wrong supposition, we shall finally rectify. But for this initial stage, we assume that only this A molecule, which is our reference molecule, is moving with this average speed c bar, and all other molecules are at rest, and they are at their own position in space. So this molecule, suppose this is one molecule, when this molecule is here, means center within this heat cylinder, it just heat. Or if you consider this another molecule, suppose this molecule is situated here, it is the center. Means center of this molecule is outside of this heat cylinder. So this molecule will not collide with our moving molecule A. So this molecule we can say just miss to heat. Just miss to heat. The molecules which is here at this position certainly will be collided with this A. This molecule which is here, or this molecule which is here, this molecule which is here, all the molecules will be colliding with this running molecule or moving molecule A. So if we consider the number of collisions made by this molecule A in unit time, maybe taken the unit time is second, how much, what will be the number of collisions made by this single molecule in unit time. So this molecule in unit time moves a distance c bar. So c bar, so this heat cylinder have an area of cross section pi sigma square, and the length of this heat cylinder is c bar. And the molecules which are staying within this heat cylinder they will be collided with this moving molecule. So the volume, volume of the heat cylinder equal to pi area into the length of this cylinder. This is the volume of this heat cylinder. Now we see how many molecules are included, or centers of how many molecules are included within this heat cylinder, within this volume. Say N dash is the number density of the gas molecules. Number density of the gas molecules at a given temperature pressure. This number density means the number of molecules in unit volume of this gas, certainly at a certain temperature and pressure. So if we multiply this N dash with this volume, we shall get the number of molecules within the heat cylinder. And this is equal to pi sigma square C bar and N dash. This is the number of molecules whose centers are present within this heat cylinder. So all these molecules will be suffering collision with this moving molecule A. So collision number, this is the collision number, means it is the number of molecules, it is the number of collisions made by the single molecule with the other molecules in this gas in unit time. So all the molecules whose centers are lying within this heat cylinder, they will suffer collision with this single molecule A. So this one, this we can say Z1. Z1 is the collision number, and this collision number is pi sigma squared C bar N dash. Since all the molecules here will be colliding with this running molecule A, so this is the number of collisions made by this single molecule A in unit time. But we like to modify this formula. We have taken one wrong supposition. Say this molecule is moving with this average speed c per, and other molecules are at rest. This is not the actual picture. In real picture, what is the real picture? All the molecules are moving with this average speed c bar according to the assumptions. So this c bar is to be modified. If all the molecules are at rest, then this molecule is having this average speed c bar. If all the molecules are moving with this c bar average speed, then what will be the speed of this molecule A, and this speed of this molecule A will be the relative average speed. So C bar is replaced by pi sigma square C relative bar and n dash. C bar is replaced by the C relative bar. When all the molecules are moving with this average speed C bar, this molecule is moving with this C relative bar. Next, we shall have to calculate or find out the value of C relative bar. You know the molecules, say this molecule, suppose this molecule is this molecule here, this molecule also in this case colliding, and actually molecules can these molecules can collide in all angles, all possible angles within the range of 0 to 180. So consider it is a planar. Molecules, whenever there will be binary collisions, it will be plane. Molecules will move in this plane. So the range of this angle of collision will be from 0 to 180 degree. So, or better, we can consider two types of the two extreme collisions, of course binary collisions. We are considering the binary molecules, two-body collisions, not considering the three-body collisions or four-body collisions. I have already told three-body collisions are rare and four-body collisions are impossible. So two extreme collisions, two extreme collision. One is this molecule and here is another molecule coming this way, and this is the head-on collision. Means both the two are moving in a straight line and colliding. Very fatal collision. So in this case, it is called the head-on collision. Head-on collision. And in this case, theta equal to 180 degree. 180 degree. Another extreme collisions, another type of extreme collisions. So this is one molecule, this is another pi sigma square C relative bar and ns. Another extreme collision. This is one molecule. This is another molecule. It is going this way. It is also moving in this way. It is center. So this sort of collision is called the side-on collisions. Here one molecule is running, one molecule is moving, so they are touching each other sideway. So this is called the side-on collision, and theta equal to 0 degree. In this case, C relative bar equal to 0, and in this case, C relative bar equal to twice C bar. So what we can do? We can take an average between the two extreme collisions. Here the theta is 0, here the theta is 180. So the average of these two angle of collisions may be taken 90 degree. 0 plus 180 degree equal to 90 degree. Whenever they are taking this average between the two extreme collisions, then suppose this molecule is coming here, this molecule is coming in this direction, and say this is also moving with this C bar. This molecule is also moving with this average speed C bar. Then resultant average speed will be this one, and this is the C relative bar, average value, and this average value, it is C bar, so it will be root over of C bar square plus root over C bar square, and here also C bar square equal to root 2 C bar. So this C relative bar is to be replaced by root over 2 C bar. Means this molecule is moving with this relative speed root over 2 C bar, while the other molecules are moving with this average speed C bar. Now, replacing this one, this number of collisions or collision number Z1 or collision number Z1 equal to root over 2 pi sigma square C bar enters. Pi sigma root over pi sigma square C bar and enters. So this is the expression. This is the expressions of the collision number. Means this is the number of collisions that one single molecule will make with other molecules present in this gas or around that molecule in unit time. Now we like to explain the effect of temperature or pressure on this Z1. Actually, if we rise this temperature, then C bar will increase, then Z1 will also increase. Means as temperature is increased, means C velocity, average speed will increase, and naturally number of collisions made by that molecule in unit time will also increase. If the pressure is decreased, pressure is increased, suppose pressure is increased, means volume is decreased, and in this case number of molecules or the thickly populated, and collision number will also increase. But we like to show the dependence of temperature pressure effect of effect of T and P on Z1 in truly mathematical way. We know this C bar is equal to root over of 8 RT by pi m. T the temperature, R the molar gas constant, M the molar mass of this gas. And say N dash, already we have shown it is equal to P into Avogadro number divided by RT. This could be calculated. Say for taking the ideal gas equation, and this is PV equal to nRT or equal to A number of moles, means number of atoms present in this gas divided by Avogadro number into RT, or P equal to N by V into RT divided RT by Avogadro number. So this one is the number of molecules per unit volume, and it is N dash. So this is equal to N dash into RT by NA. Or say N dash equal to R equal to P into Avogadro number divided by RT. Or you can say P divided by R by Avogadro number into T. R by Avogadro number is also, you can write this P divided by KT. K the Boltzmann constant. K the Boltzmann constant, or this gas constant per molecule. So, if we put here in the expressions of this Z1, so Z1 equal to root 2 pi sigma square. Sigma square is constant for a gas. It is not affected appreciably with the change in temperature and pressure. So collision diameter we can assume as fixed constant for this gas. Of course, the different gases will have the different collision diameters. And instead of C bar, we can write a root over of 8 RT by pi A. And in this case, N dash equal to P divided by KT. So if we extract a temperature or pressure and others are constant for a gas, then it will be constant into P and divided by root over P. This is Z1. And from this expression we can actually numerically can show how the temperature and pressure will affect this collision number. So here J1 is proportional to P when T is constant. If you keep this temperature is constant, then Z1 is directly proportional to P. Temperature constant means C bar constant. If you increase this pressure, then N dash is decreased, volume is less. With increase in pressure, volume is less. So N dash is increased Z1 will also increase. If you double this pressure of this gas, if you double the pressure of this gas, then collision number will also be doubled. So again, another thing is that Z1 is proportional to 1 by root over T when P is constant. When P is constant, if you increase this temperature, then volume will increase. And when volume is increased, the number of collisions made by the single molecule in every time must decrease. So Z1 is inversely proportional to the root over of T. But if T and P both changes simultaneously, temperature and pressure both are simultaneously changing, then instead of P is proportional to T. Temperature pressure both are changes, both T and P both change, both varies, both changes, then volume remains fixed. You know, in a gas there are three. For a fixed amount of this gas, there are three parameters: temperature, pressure, and volume. And these three variables you cannot change simultaneously. Only two are independent variables. That means you can change according to your own choice, but the third will be fixed. It will be dealt in phase rule more elaborately. So whenever the temperature and pressure both are changing, both are keeping with our choice, then volume is fixed. And when volume is fixed, when V is fixed. So pressure is proportional to T. So here we can write instead of P, we can write a T. So it will be some constant, say constant, another constant. Here T and here root over T are equal to constant and root over T. Means whenever T is increased, temperature pressure both are increased. In this case, with the rise in temperature, this Z1 also increase. So this is a much more mathematical way to show the effect of temperature on this collision number. When T is constant, T is constant, the Z1 is directly proportional to P. Means if you increase this P, then Z1 will also increase. If the P is constant, then Z1 is inversely proportional to root over of T. Means with the increase in T, volume will increase and Z1 will decrease. And when T and P both varies, then P proportional to T. Whenever T and P both are changing according to our own choice, then volume is fixed. So whenever volume is fixed, then volume is fixed, then P is proportional to T. They are related, directly related. With increase in T, pressure also increased. So instead of P, we can write here T by root over T means root over T, and means whenever T is increased, Z1 is increased. So when temperature, pressure both are varying. Now we are coming to another aspect of our discussion. mean free path, and it is mean free path, it is symbolized by lambda. Mean free path means the distance travelled by a molecule on an average without suffering collision, with other molecules present in this gas. So, or it could be said that the distance between the two successive collisions. And whenever the molecule moves, it may be the chance, just at the start of the movement of this molecule, it suffers a collision. In that case, the free path is 0. Or this molecule can manage to move a long distance without suffering collision. In this case, a free path for that molecule will be very high, tending to infinity. So this free path will change, will vary from 0 to infinity. Say one motorcycle rider, whenever just he starts, made an accident, or in that case, this free path for that rider is 0. But this vehicle, motorcycle rider can move a long distance, or throughout his life he moves a much more distance without suffering any accident, suffering any collisions with other substances around him. In that case, free path of that motorcycle rider is infinity. So this free path can range from 0 to infinity. So we shall talk about this mean free path. And this mean free path could be expressed as C bar, average distance travelled by the molecule in unit time, and the Z1, the number of collisions made by that molecule in unit time. So this C bar by Z1 will give you the mean free path. Since it is the average speed, so lambda is also the average free path or mean free path. Say the molecule starts from here. Here makes one collision, here makes another collisions, here makes another collisions, here 4 and 5. And this is the, suppose 10 centimeter per second the velocity and the speed of this molecule. 10 centimeter per second, say for example's sake. And within this distance, the molecule suffers 1, 2, 3, 4, 5. Means 5 collisions per second. It is the collision number. It is the average speed. So this 10 by 5. So lambda in this case will be 10 centimeter second inverse divided by 5 collisions. Second inverse equal to 2 centimeter. So 2 centimeter will be the mean free path of this molecule It is moving 10 centimeter, average speed is 10 centimeter per second, and average collisions of this molecule per second is 5. So in this case it is also the ratio of these two. Now we can put the values instead of C bar, here it is written C bar, and Z1 root over 2 pi sigma squared C bar x, or lambda equal to C bar cancelled, 1 by root 2 pi sigma square index. So this is the expressions of this mini free part lambda. So lambda you can calculate if you know the collision diameter of this molecule and the number density. Number density depends on temperature and pressure. Now we see how the effect of temperature pressure on this mini free part. Effect of T and P on lambda. Say lambda equal to 1 by root 2 pi sigma square, it is constant, and instead of n dash we can write P by Kt. Here P by Kt means here K will be go outside in numerator, and here T by P. So within this bracket all the terms are fixed for a gas. So we can write constant and T by P. Means if lambda is proportional to T when P is constant. P is constant. Means if you increase this temperature, pressure constant. If you increase this temperature, then volume will increase. Then free path, mean free path, or the distance between the two successive collisions will also be high. And again lambda is proportional to 1 by P when T is constant. Temperature, whenever the temperature of this gas has been kept constant, lambda is inversely proportional to P. Means if you increase this P, volume is decreased, lambda is also decreased. Say, that means inversely proportional. Lambda equal to constant into T by P. So one very simple questions asked in examination. At constant temperature for a gas, you just draw one diagram, lambda versus P. So lambda versus P is if this is lambda and this is P and this is volume at constant T. At constant T. You know P is independent variable, and independent variable is plotted along this x-axis, and lambda is dependent variable dependent on P, so lambda is plotted along this y-axis. So what will be the nature of this curve? Or you can say lambda into P equal to constant at a given T. So lambda versus P, like the Boyle's law, PV equal to constant, this will be rectangular hyperbola. Rectangular hyperbola. Now one thing I can mention here. Say in this case temperature and pressure both are varying. Both you are changing according to your own choice. Then V remains fixed. When V remains fixed, temperature, pressure both are changing. Among these three, you can vary these two parameters, and third will remain fixed. So whenever you are varying this pressure and temperature, V is fixed. V is fixed for a definite amount of this gas. So in this case, this P is proportional to T. V is fixed for a given amount of this gas. So T by P is constant. Means lambda will remain unchanged. If you vary the temperature and pressure simultaneously, this is the very important question asked in several competitive examinations. Now I will give you one problem. Z1 equal to root 2 pi sigma square C bar and A dash. On the basis of these two formula, I like to give one problem, and a problem is given to you for your exercise. And in my next class, I will solve this problem and find out the several informations. The problem is for oxygen gas at 25 degrees centigrade and 1 atmosphere pressure, estimate the number of collisions made by a single oxygen molecule in 1 second time. 1 second time means it is the Z1 condition. And also find the mean free path of the gas, of the oxygen gas at this of this oxygen gas at the same temperature, at this temperature pressure. Given, what is given? Given the bond distance of oxygen molecule equal to 1.2 angstrom. Sigma is not given. Instead of sigma, here the bond distance of this oxygen molecule is given. So, and all other things, if you know the temperature, pressure, then all these C bar and N dash you can calculate, put here and here and here, you can find out. But sigma, how can you calculate this sigma? Say, here is one oxygen atom, here is another oxygen atom, it is the center of, and it is the center of these two oxygen atoms in a molecule. So this is molecule. This is one oxygen molecule. Then other oxygen molecule, say this is another oxygen atom, this is another oxygen atom, it is centered, and it is another molecule. So this oxygen molecules are colliding, and the sigma will be, this is the center of this oxygen molecule, this is the center of this molecule, and the distance between the two centers, between the centers of two oxygen molecules, this is sigma. This is sigma. And it is given that bond distance, this is the bond distance. Bond distance. This is bond distance. Bond distance of this oxygen molecule, this is another bond distance of this oxygen molecule. Then how the bond distance could be connected with this sigma value? You see, from this to this, so this is sigma. Here to here. So this one is half of the bond distance. So this one is another half of the bond distance. This one is another half of the bond distance. This is another half of the bond distance. So 1, 2, 3, 4. This is 1 and 2 and 3 and 4. 4 half bond distance. 4 half bond distance is equal to the sigma. Here to here, 1 half bond distance, half bond distance, half bond distance, and half bond distance. So 4 into, so 4 sigma equal to 4 into half bond distance equal to 2 into bond distance. So sigma is equal to 2 into bond distance is given 1.2. So this is 1.2 angstrom. This is equal to 2.4 angstrom. So sigma is given here. Sigma is calculated as 2.4 angstrom. So all the values are given, sigma, C bar, and N dash for this gas at 25 degrees centigrade, 1 atmosphere, normal temperature, pressure. You have to find out Z1 and lambda. In my next class, I will explain the two values and what are the other informations. What are the other information we can calculate, we can find out from these two values of the oxygen gas at this temperature and pressure. So it is all about today's lecture, and thank you all for watching my video. In my next class, I will explain the solution to this problem and the frequency of intermolecular collisions with like molecules and with unlike molecules. That will be a little bit tough. Next class, these topics will be included. Thank you all again.